question I need to talk about. That's our midterm. So you need to, think about. Yeah. But I need to change a little bit on our syllabus. Yeah. Let me bring up the calendar. This month, March. So we're here. All right. Yeah. So we're here. All right. Do you still remember what is the deadline for our homework assignment number 1? Deadline? 11. Yeah, good. Yeah, Tuesday, 11. Yeah. All right, so I plan to, so here, the first thing, I plan to set a midterm March the 19th, Wednesday, this day. Our original schedule is this day, as I remember, all right? 1 week earlier, original, yeah. Because based on our current, because we need to, the deadline is 11th, Tuesday, yeah. After that, I need to give you 2 review sessions. Preparing for the midterm, I need to do review, okay? So 12th, Wednesday, first review session, all right? 17th, Monday, second review session, okay? Then, 19th, Wednesday, that's our midterm in class, all right? Yeah, different from 1 week after our, initial, I planned, because I estimate, it may not be very accurate. So I want to postpone by 1 week, okay? Midterm, test day, postpone by 1 week. Yeah. So to let you prepare better, okay? Yeah, spend more time. Yeah. So these 2 sessions, first session I need to discuss all the quiz questions. Yeah. I need to go through all the quiz questions, okay? Yeah. So then the second session, I need to go through the homework assignment number 1 questions, yeah, because I need to a few days grading. Yeah. So then this Monday, yeah. Oh, before this weekend, because you need to prepare weekend, I post the answer solution, okay? Yeah, you study answer solution. But this Monday, because when you use my solution file study, you may have some questions. So Monday, when we do review, then I can answer your questions, okay? So I can only select a relatively hard question to explain in class. Yeah. But if you have any question, you just, bring up in our Monday review session. Yeah. So I can explain your questions. Then, 19th, yeah, let me see. Yeah, let me think about, because the 19th, right, because the question, remember the question, when we do test on 19th, still there are some details we need to work it out. Details. We need to work it out. Yeah, because, all right, the question, the detail. So the last thing I want to explain regarding the test question details. Because there are another online class in parallel with your class. Yeah. So I also need to do the midterm, online, that class, at the same time. But I want to, so your in-person, online, different environment, But when I do the test, I want to make it, relatively in a fair environment. Do not put you in too much disadvantage. Right? Because relatively you use less time than the online group of students. So I want to try my best to, level the ground. You know, so do not put you in too much disadvantage. Okay, yeah, because you have some time-wise, you have some disadvantage, right? Yeah, yeah. But I try to do something to make you, you know, get better. Yeah. All right. The first thing, the total number of questions, 25 questions. Yeah, just like our homework assignment, 25 questions. Okay. But I split into two parts, part A, part B. Part A, part B. Yeah. Part A, 10 question, concept questions. Yeah, you know, our usual, you know, quiz, just like a quiz. Yeah. Part A, it's a quiz. Yeah. But I run part A as a regular quiz. Give you more than 1 week to complete our regular quiz, right? Yeah. Yeah. That's part A. Yeah. So you do it at home. Yeah. So save your class time. Save your time used in class. Yeah. You know, to level the ground. Try to, you know, level the ground a little bit. Okay? Yeah. The part A. Yeah. Part B, then, remaining 15 questions, part B. Yeah. Part B I want to do this way. Part B, total 15 questions. I split in two parts, also two parts. Yeah. The first part, 10 questions. First 10 questions in part B. That's the basic questions. Basic, okay? Yeah. So not too hard, okay? Yeah, I mean, just the basic knowledge you need to know, yeah, but not trivial. You need to do some work, okay? Not too hard, not very challenging, okay? Not very challenging, yeah. But you need to do some non-trivial work, okay? Yeah, yeah. So that's the 10 questions, yeah. So you have to complete in the classroom, okay? 75 minutes. That part you have to complete in 75 minutes, 10 basic questions. Yeah. Then the last 5 challenging questions. Okay? Last 5 relatively challenging questions. Yeah. I also give you in class, so the total 15 questions. If you have time, you can work on that. All right? If you do not have enough time, you can leave it out. When you get home, I post the last 5 questions to you. So you can do the last 5 challenging questions at home. Yeah. In this way, I try to level the ground. Yeah, so your class, online class, because online class, I will give them 25 questions altogether. Yeah. Although I split as quiz, part B. But part B, 15 questions altogether. Okay? But for you, you need to complete the basic part in this classroom in 75 minutes. That's my plan. Okay? Try to be fair. All right? Yeah. Yeah. All right. So, yeah. So that's the midterm. Okay? All right. Then we start half page last time. Problem number 9. Count binary digits. Yeah. So let me continue the story. So we were here last time. Yeah. All right. So this place. Yeah. So let me change my pen color. Yeah. Right. Yeah. Now, the remaining part, we need to solve recurrence relation. So this one, recurrence relation. Yeah. Yeah. Initial condition, yeah. Then, how to find a solution mathematically. Here we need to solve this. This is a math problem. So it's not a CS problem. CS where we write a recursive function. Then you get a solution. Math problem, we need to find a formula for this A function. So what is its formula? We need to derive its formula. Yeah. So it's a math problem, right? Yeah. But we use the problem solving here. So you can see So problem solving strategies. Yeah. So we need to study problem solving. Yeah. Method, techniques. Yeah. All right, so here. Question, how to handle floor function? Yeah, because in this recursive relation, there is a floor function, right? Yeah. That's the problem we do not feel comfortable, right? Because this floor function adds some complexity to the formula, right? Add some complexity to the formula. So the first question, how to handle the floor function gracefully? How to handle the floor function gracefully? Yeah. Okay, yeah. Let's answer this question first. Yeah. All right. Floor function. So there is a, because we know sometimes this floor function equals the fraction inside that brackets, right? Yeah. Sometimes equal, sometimes not equal. Okay? Yeah. So we need to consider those two cases. Yeah. All right. When n is an even number, that floor function, you just remove the floor function, you get the same thing. Yeah. But when n is an odd function, you need to modify the value slightly. So what do you get? N minus 1 divided by 2. Yeah. Truncate half integer, right? You get a half, because you divided by 2, you get a half integer. So you truncate that half integer, 0.5. Yeah. All right. Then it's in the point, so we need to apply our strategy. Yeah, I mentioned something before. Here, there are two cases. Which case we should work on first? Well, we have two cases. You have freedom to choose. Which case you like to choose first? Even case or odd case? Even, yeah. Carry even. Matthew, do you want to choose odd case first? Yes. Yes, easier. Yeah, so that's the simple point. So we call it the golden rule, right? Yeah, so when you have multiple cases, you always choose easy or easiest case first. Yeah, that's simple. So let's consider even number n first. Yeah. All right. What do you wish to have? Now, we can simplify the equation, right, with the even case. So what we will get, yeah, so well, n even, yeah. But when you go to the next formula, yeah, because recursion, we need to move to the second level, right? Yeah, yeah, next equation. But this time, even case, so this part, we can remove the floor function directly. But how about n over 4? Another floor function. We got some problem, right? So what do you wish to have? Yeah, because here I ask you wish to have. You can make your wish, okay? Yeah, so if you have chance to make a wish, so what do you want to wish here? Matthew?
Divided by 4 is still equal.
Not too much. N is divisible by 4. How about that? Or n is a multiple of 4. How about that? Yeah. Now you told me n divided by 4 still even. More than necessary, right? Yeah, because n over 4 we only require, it's an integer. Now you told me we require an even integer, not just integer, even integer. Yeah, yeah. Probably you go one step further, because the next equation you need divided by, divisible by 8, right? Yeah. But keep doing. If n is not a power of 2, if n is not power, sooner or later we will hit that floor function problem, right? Sooner or later. But if we assume n is the power 2, we can go all the way to the end without any flow function sticky problem, right? Yeah. Yeah. So our best wish, we assume n is power of 2. So our first special case, the easiest first special case, we assume n has the form of power of 2. Yeah. If people ask you why you can't make that kind of aggressive assumption, you can talk about that golden rule. Okay? Yeah. Because golden rule, when we do problem solving, we can find simpler versions of the original problem to work first. Yeah. Because later we will fix the gap, right? There is a gap between the special case and the original version, but we will fix that gap later, right? Yeah. All right, so that's next. This time we assume n equals 2 to the k, power of 2. Yeah, yeah. This time we can remove all the flow functions. Yeah. In all the levels of equations. Yeah. There are multiple levels of it. Everywhere we remove flow function. Okay, let's do the work. Yeah. New recurrence relation. You can see in this new recurrence relation, all the flow functions are gone. Yeah. Yeah. So that's, you know, yeah. We can work on the normal equations without flow functions. Yeah. Let's do the work. The first equation, yeah, left-hand side, right-hand side, like this. Yeah. Second one, see, yeah. So we just reduce the exponent number by 1. Yeah. Divided by 2, reduced by exponent number by 1. Yeah. And so on. Okay? Yeah. All the way down, but we need to stop at the lowest level. We need to stop somewhere. Yeah. So what is the last equation in this sequence? Yeah. Yeah. Last equation, yeah, because your initial value, a of 2 to the 0 equals 1. This is your initial value. So the last equation, this part, this should correspond to 2 to 0, and this 2 to the first. That's the last equation. Okay? So let us write. Last equation is like this. All right. Then we need to find the formula. Yeah. Because so if you examine all these formulas, first, can you tell me how many equations do we have here? You need to count. You need to tell me. Count the number of equations. Yeah. How many of them here? Yeah. Can you try to, you know, find a way to count it? Yeah. Try, everyone. Try it. And yeah. So you said K. How about you? Matthew? K or K plus 1. You want to say K plus 1? No? K or K plus 1? So because one of the two must be wrong. So we need to determine which one is correct. Yeah. K1 or K plus 1? Ethan, you want to try? Which one you want to say, you know, better? One of the two cases? K better or K plus 1 better? Here, let me remind you a little bit. We learned, I applied that method several times, counting by reference. Can you still remember? When we do the counting, can we find appropriate reference objects? Yeah, we just count the reference objects. Can you find the reference object, Ethan, here? When you do the counting? Yeah. Each equation you associate with appropriate reference object. And then you do the counting on that reference object. The first equation, can you associate with that superscript k. Yeah. Each equation, can you associate with appropriate superscript number, right? Yeah. That's one-to-one correspondence. The last one associate with this one. Okay. Now you just count the reference objects. How many reference objects do you have? Can you see that easily? Is that easily? Because you do the counting from 1 through k, right? That's k. Consecutive integers from 1 through k, the number is k. Yeah. Although you can use here, because people may argue, you can use these numbers as a reference. Yeah, that's fine. But you need to count from 0 through n minus 1, k minus 1, right? The same number, but this column is slightly better, right? Yeah, from 1 through k. Yeah, more direct, okay? Yeah. Counting by reference. Yeah, so I mentioned this, at least 3 times. This method, at least 3 times. Well, you need to do the counting. Yeah. Find appropriate reference objects to do the counting. Okay, all right. Yeah. So k, why I ask you k or k minus 1? Yeah, because when you add up all these equations, you need to add up all these ones. How many ones do you have, right? Yeah. Yeah. After you know the number of equations, you know number of ones you need to add. Okay? You have k ones. Yeah. But remember, initial value another one, right? Initial value another one. So k plus 1. K plus 1. Okay? All right. Other terms, cancellation. Yeah, you can see the cancellation like this. Yeah, this kind of cancellation. Yeah. Yeah. Then at the end, summary. Yeah, you get it. A of 2 to the k equals k plus 1. Yeah. But you need to go back to the n representation, right? Yeah, because this k is an intermediate variable. It's not our original variable. Yeah. So we need to go back to the original variable, n. Yeah. So 2 to the k will replace it by n. The result, a of n equals 1 plus, what's the k? Log base 2 of n. Yeah. So, because k equals log base 2 of n. Yeah. So you get explicit math formula. This is explicit math formula. Nice formula. Very simple, right? Yeah. Yeah. But this formula, it is only true when n is power of 2. But we need a formula for the general case, right? Yeah. Yeah. Not power of 2. Yeah. Power of 2, that's your simplest case. It's not the general case. So our goal, we want to get a general formula that covers the general n case. What you should do. Now, next step, we go to the general case. Yeah. Fix the gap, right? We need to do there is a gap. So this special case formula and the general case formula, there is a gap. Now we need to work on the gap part. Yeah. What do you plan to do? Anyone has an idea? What do you plan to do? Olivia, do you want to say something? Anything? 1 plus floor. Oh, good. Yeah. Can you explain why floor? Why you want to do that? Floor. Yeah. Yeah. Here, because we want to do problem solving. When we do problem solving, our logic thinking is very important. Okay? Logic thinking is very important. So when you do everything, you need to follow your natural logic. We need to follow our natural logic. So here, when you come in this guy, I spend a lot of time to give you a whole story about problem solving because I want to give you training on problem solving. Okay? I hope you, after the training, you can do the problem solving similar to this. Use the natural logic. Yeah. So we apply strategies. We apply methods, different methods, techniques. In that way, you need to go through that kind of training. Okay? Here we need to do the training. Yeah. Remember, we did a strategy before called the guess and verify. Yeah, remember that? Yeah. String matching problem. So when we try to figure out a formula, we guess first, but we do not know our guess is correct or not. We need to verify it. Okay? To get it right. Here we are in a situation. Now, because when we move from the special case to the general case, we do not have an idea where to go, but can we guess? Right? We don't know the destination formula, the final version of the formula. But can you guess? Yeah. Because our A function, it's a number of additions, right? The meaning is number of additions. That number should be an integer, right? Yeah. But if we look at the right-hand side, this log base 2 of n for the general n, is this expression is an integer for the general case? Yeah, not power of 2 case. Okay? So that expression may not be an integer, right? No. If it's a non-integer, then this expression cannot be used directly for the general case, right? But if it cannot be directly used, can we convert it to the integer expression? Right? Yes. We can convert it to integer expression. Yeah. What is the easiest way, the simplest, easiest way to convert a non-integer expression to an integer expression? Okay. Simplest, easiest way. Yeah. 2 ways. Floor functions and the ceiling functions. Right? Yeah. So one way you apply ceiling function. The second way you apply floor function. Right? Yeah. One of the two. Yeah. So that's your guess. Yeah. Your guess. Yeah. Because we want to make some reasonable, simple guess. Okay. So your guess is you apply these 2 integer functions. Yeah. Floor function, ceiling function. So there are 2 versions. Which version you want to take? So here, we need to choose one of the 2. Yeah. Yeah. It cannot be both correct, right? Yeah. Yeah. At the most, one is correct. Yeah. So you need to eliminate one. Yeah. Matthew, how to choose from these 2 versions? Do you have an idea? How to choose?
We're going to cast just start with the ceiling function.
Hey.
Guess and verify.
Can what?
Guess and verify.
Oh, yeah, verify. So we made a guess. How do you verify it?
Put it in the order and then see what comes out.
Good. Yeah, that's simple, right? Just plug in some simple numbers and see which version you get a contradiction. We can eliminate, right? The one with contradiction, we can eliminate. The one without contradiction, we take it. Okay? All right, let's plug in some simple number here. All right. Yeah. All right. So when we plug, yeah, so here, 2 versions. All right, so here I use this space. Yeah. And let's see. We want to choose some function that's not power of 2. If it's a power of 2, then both function returns the same value. It's not a power of 2. Which number do you want to choose? Simple. You don't want to choose a hard one, right? Yeah. 1025 and 34. You don't want to choose that. Do you want to choose if I ask you to choose, which number you want to pick? 3. 3 is the best. Simplest. Non-power of 2. Simplest non-power of 2 number. Okay? Yeah. The best is 3. You plug in 3. This version what do you get? Seeding function. Log base 2 of 3 seeding function. What's that number? 2. This is 1, right? Yeah, 1. But for the 1, because you need to plus 1, okay? Yeah. This one, after you plus 1, you get a 3. You get a 3. This way, after 1, you get a 2. What is, if you represent 3 in binary format, what's that representation? Binary. 1, 1. Yeah. 3 equals 1, 1 base 2. Okay? The base 2. 1, 1 base 2. How many digits? Count. 2, right? Yeah. 1, 1. 2 digits. Yeah. Oh, sorry, bits. 2 bits. Yeah. 2 bits. So that is the answer, not 3. So it's wrong. You verify it. That's the verification. Yeah, simple verification. That means seeding function version, we can eliminate it. Okay? Floor function version, we can take it. Yeah. So we use this simple example, we can practice that our guess and verify strategy. So you can see, yeah, many simple strategies we learned before. Yeah. So we have many chances to practice. Okay? Yeah, yeah. I hope after I use this way, let you practice 4 or 5 times, so you can apply it by yourself. Yeah, yeah. Naturally, yeah. So because we practice so many times. Yeah. All right. Let's continue the story. Next, B.2, variable size. Oh, yeah, this is a new question. Before that, let me say something. Let me make some comments before we move to next topic. All right. Now, this is our guess, right? And this formula, for the general case, it's hard to verify it, right? Guess and verify, but this time we need some powerful method to verify, right? The question, how to verify it? Yeah, because to verify, it's not as like the simple case we plug in 3. This time you plug in 5, 7, 9, 11. Even if all of them true, you cannot say it's true, right? Yeah. Mathematically, you cannot, even after you practice 1 million numbers, you cannot say it is true, right? Yeah. Mathematically, it's not a proof. Even after 1 million times, you try, always true, still, because there is possibility, it may not be true, right? Yeah. How do you 100% sure to verify it is true? Yeah. Yeah. So here you need some advanced tool here, powerful tool here. So we need to use some powerful tool to verify it. What's that powerful tool? In your discrete math course, you learn it, discrete math course. So that's why, we list that as a prerequisite, because we need to use a lot of knowledge from that discrete math. Okay? Yeah, here, let me mention that. Mathematical induction. Mathematical induction. This powerful tool. Okay? Yeah. So the next step, if you want to show this formula is correct, you have to apply the mathematical induction to prove it. Then it is a rigorous proof. Yeah. Nobody can argue. Okay? Yeah. It's incorrect. Nobody can argue. Yeah. Because this tool guarantees if you apply mathematical induction correctly, 3 steps, 1, 2, 3, correctly, then it must be 100% true. That powerful. Okay? Yeah. So here I can do it. I can do it here. Yeah. But I want to skip it. I want to skip it. Okay? To save some time. Yeah. Yeah. The reason, yeah, because in our next part, next topic, Fibonacci numbers, we will have second chance to apply mathematical induction. So I just do once, okay? Yeah, so this class, I only do mathematical induction one time, just refresh your memory, okay? Yeah, telling you that that is a powerful tool. So here I save it, I skip it, you know, because in that Fibonacci formula, we will do the review on mathematical induction. Yeah. So I do not do here. Okay. Otherwise, I need at least 20 minutes to complete it. If I do it, I need to use 20 minutes. Yeah. So now I combine these two proofs. I just do one of the two to show you how to apply mathematical induction. Okay. All right, yeah, so we move to next topic, B.2, variable size reduction. This time, from the name, you can see every time when we reduce the problem size, the amount of reduction could be different. Sometimes we have more reduction, sometimes we have less reduction. Variable size reduction. Okay, yeah, so first let's look at the question. Our problem number 10, greatest common divisor. Yeah? So it's a, you know, simple, yeah, but very important problem. Yeah, people call it GCD. Yeah. Okay. There is people even use the GCD as the function name. Okay. GCD function. Yeah. So you can calculate the greatest common divisor of 2 given integers. Yeah. So here, let me give you the problem first. Given 2 non-integer values m and n, we allow m and n to be 0, but we do not allow them both 0. We do not allow m and n both 0. One of the 2 could be 0, so we allow that case. But we do not allow 2, both 0. So why? Yeah, I can explain later. The goal, find their greatest common divisor, GCD of m and n. Greatest, yeah. The meaning, yeah. So you know the meaning immediately, okay? So I do not need to explain what is the greatest common divisor, right? The meaning, yeah. So you know it. Yeah. All right. Here I like to explain why both 0 is a problem. 0 GCD. Yeah. GCD function, if we apply, so you will get, you know, not defined. It is not defined. Okay? So you get problem. Yeah. You cannot define any appropriate value. Yeah. Because people tend to use 0, right? Yeah, because you see, you know, 2 0. So you get a strong impression. You like to put a 0 there. Yeah, but actually, if you examine the details, you will see. You cannot put any number there. Yeah. If you put any number there, it's wrong. Okay. The problem is, this 0 is very special. 0 number is a very special number. Okay? Yeah. 0 number is different from any other number. It is very special. Why it is special? Do you know 0 is a multiple of 1? Do you think it's true? 0 is a multiple of 1. Or 1 is a divisor of 0. 0 over 1 equals 0. This is 1 at the denominator, so it's a divisor. But this is integer, right? This 0 is an integer. The quotient is integer. Can we say 0 is a multiple of 1? Right? Is 0 a multiple of 2? Is 0 a multiple of 3? Yeah. So 0 multiple of 1, 2, 3, any integer, and 0 is a multiple of that one, right? Yeah. All these positive integers, 0 is a multiple of all of them, right? Can you find the largest one? Can you find the largest? Yeah, because our second number also 0. So you want to find the second number, so they share all these divisors. Which one is the largest divisor? There is no largest divisor, right? All these positive integers, they are divisors of 2 0 numbers. They are common divisors of 2 0 numbers, right? But there is no largest common divisor. So it's not defined. GCD of 0, 0, undefined. Okay? That's why here we do not allow it. Okay? We do not allow it. Yeah. Yeah. All right. Yeah. So now, solution. Yeah. So we need to consider the solution. Yeah. For the solution, here. Yeah. I think most of you, you did. You solve questions like this when you were in the middle school, right? Yeah. So you can recall a little bit. In your middle school, did you solve, at least did it once, twice, okay, a few times, right? Yeah. Here, let's review the middle school solution. Yeah, there is middle school solution. Yeah. So let's review a little bit. Okay. All right. Yeah. So our first method, middle school procedure, step 1, find the prime factorization of the first integer n. Prime factorization. Okay. Yeah. You know the meaning, right? Prime factorization. Step 2, find the prime factorization of the second integer n. All right. After these two steps, find all the common prime factors. Yeah, because you compare all the prime factors from these two numbers. Yeah, so you can get a common part, right? Yeah. So the step 4, compute the product of all the common prime factors. Yeah. So you take the largest common part, right? Then you do the product. So you get the answer. So this is the middle school solution. Yeah. Then, let's see. Yeah. Here, let me use a simple example to show you all the 4 steps quickly. Yeah. All right. Yeah. All right. So example, we want to find a GCD of these two numbers, 60 and 24. Yeah. Let us do prime factorization of 60. So we get 2 squared times 3 times 5. Yeah. By observation, yeah, use our eyes, we can get that, right? Yeah, not that hard. Yeah. Then 24, by the observation, we can get 2 cubed times 3. Yeah. Yeah. The last step, the step 3, common divisor part. Okay. Power of 2, the largest common factor for this part, 2 squared. Yeah. Common factor, largest common factor for regarding the power of 2 factors. Yeah. Power of 3, the factor part, largest, just 3, right? Yeah. Yeah. So 2 times 2 squared times 3 equals 12. Yeah. So there, our final result, GCD of these two numbers equals 12. That's the middle school way. All right. This way, let's do the summary here. This method, you can see, it relies on prime factorization, right? This method this solution, let's say this solution, relies on prime factorization. Yeah. 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 All right. Yeah. But the question, in our algorithm class, after we discovered an algorithm, so we need to ask ourselves this question: is it a good algorithm? Yeah. Do we still have some room to improve this algorithm? We need to ask this question. Yeah. Yeah. All right. Yeah. 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 To answer this question, you need a lot of experience. Yeah. So usually, most people, they do not have enough experience to answer this question. Yeah. So the most important thing is about this prime factorization. Do you have an idea how hard is the prime factorization? That's the main question. Yeah. How hard is the prime factorization? The general prime factor, not a 60, yeah, 25, this small number. Can you imagine if we want to do prime factorization on some huge numbers? Yeah, think about it. There are 1 million digits. How do you do prime factorization? You're allowed to use computer software. Yeah. You're allowed to use any computer software. Okay? But if we need to take prime factorization on a huge number with 1 million digits, can you imagine how hard it is? 1 million digits. Extremely hard, right? Yeah. Yeah. The final result. Yeah. Extremely slow. Yeah. Yeah. The hardest computer, supercomputer. Okay. Most powerful computer in the world. Yeah. And not just one. You can use 1,000 computers, 2,000, tens of thousands of computers, run in parallel. Yeah. To do the factorization on it. Still, you need many years to get an answer. Many years, the time you need. Here, I just give you some estimate numbers. Not very precise. Just give you an idea how slow it is. You need at least several years. Even you use a lot of computing resource, like the Google resource, okay? How many servers you can imagine the Google, a giant company, they have. Use all their computing resource to do prime factorization on that 1 million digit integer. They still need several years. Okay, that's slow. That's slow. All right? Yeah. So you can see the reason is prime factorization. This operation is extremely hard. Extremely hard. Okay? Yeah. Very slow. Yeah. Yeah. Now, can you make conclusion this method, prime factorization based method, is a good method or bad method? It's a bad method. Yeah? So it's because we don't want any of our algorithm rely on prime factorization. Yeah, that's the huge bottleneck, okay? It's a huge bottleneck, all right? So we have to find a much better solution. Yeah. All right, okay? Yeah, so the next step, we need to find a new solution. Yeah. And it has nothing to do with prime factorization technique. Okay? Yeah. Think about that. Yeah. Yeah. Here, regarding the prime factorization, many years ago, I remember I read a story. There was some competition in the world. Yeah. Some institute or some company institute, they put some big prize to the team. Yeah. So, yeah, because everyone in the world, yeah, so you can form teams to compete for that big prize. Okay. Yeah. I mean, as I remember, $100,000. Yeah. So that amount of money. So not huge. Not too much. Okay. Not million. Okay. Yeah. $100,000. Which team? So you can find the largest prime in the world. Okay? Yeah. Because when you have a number, you don't know if it's a prime or not, right? Yeah. So you can use computer, you can use all the possible resources. Yeah. Just generate the largest prime in the world. Then your team can win that $100,000, that amount. Okay? Yeah, I read that story. Yeah, 10-something years ago. Yeah. Okay. So you know how hard to determine if a number is a prime or not, right? Yeah. That's extremely hard. Okay? Yeah. Then there is a question. Prime factor. So here we know that this is a basic fact. Okay? The basic fact, prime factorization, we know. Yeah. So extremely slow. Yeah. 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 So this is the basic fact. Yeah. Everybody knows that. Yeah. Very slow, extremely slow. The next question. This property, do you think this property is a good property or bad property? No. So we know prime factorization, extremely slow. Do you feel this property is a good property or bad property? Based on your understanding. Yeah. Understanding. Yeah. The same thing. So here, you make observation. We observe some phenomenon. This is the phenomenon we just observed. Now, we need to understand this phenomenon. Okay? In our understanding, the first question is, do you treat this phenomenon, this property, yeah, property, yeah, do you treat it's a good property or it is a bad property? Can you make some comments? Amen? Good property? Good property? Oh, he says it's a good property. You said bad, right?
I mean, it's a good property, but it's not good for the solution.
Good, yeah. So, because here I'm talking about the general things, okay? You not necessarily restricted to this particular problem, okay? So, in our real world life, right? So, because in our real world life, we can do so many different things, right? Is there a possibility there is some special thing, this property becomes a good property? Here, I'm talking about that. Yeah. Although, when we calculate this GCD problem, it's a bad property, right? But can we do something different? This property becomes a good property. Anyone can think about that question? Real world? It could be, yeah, Evan, could be good. But we need something concrete to see it, right? Yeah. Yes, it could be a good property. Yeah. When you need some special application, right? Yeah. You need to consider some special application. problem, encryption. Think about that, encryption problem. When you do encryption, it becomes a good property. Why? Yeah. The reason is very simple. Prime factorization, you know, it's very hard, and you want to make the hacker hard to break it, right? That's the goal of encryption, right? Yeah. You want to make it hard for the hackers, not for us, okay? For us, we want easy, right? But for the hackers, the harder the better, right? Yeah. The harder the better. Yeah. Okay? Yeah. So now then, people, a group of scientists, so they based on, after they observed, it was so hard to decompose a huge number into prime factors, then they want to use it in the encryption theory. Yeah. Make decoding much harder to break. Yeah. Decoding. Yeah. Because a group of people, they want to, you know, decode. Yeah. Okay. Yeah. 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 So then they develop a coding algorithm. Encryption, yeah, encryption algorithm, yeah, the famous encryption algorithm. It is still used, still very popular in, you know, encryption methods. Yeah, it's called a RSA algorithm. Okay, yeah, the initial of those three scientists, the three mathematicians actually. Yeah, because that's all based on formula, prime factorization. So three mathematicians, yeah, yeah, in some, you know, top tier university like MIT, you know, like that, you know. I just, you know, impression, based on my impression, that level, okay, yeah, algorithm. Yeah, yeah. So then they take advantage, yeah. So this phenomenon, this property, they build an encryption algorithm based on this property. Yeah. All right. Here I just say a little bit. Yeah. So, you know, give you some better understanding here. Yeah. Because so here, two operations, they are inverse each other, right? Okay. You calculate product of two large numbers. Product of two large numbers. When you calculate product, it's easy, right? Yeah. So usually, so here they do not use that 1 million digits. That's too big. It's too, right? They use you know, several thousand digits. Yeah. Each number has several thousand digits. That level, okay, that level already, you know, very hard to work on. Right? Yeah. In thousands, yeah. Each number, the digits in thousands. Yeah. All right. Then, if you do multiplication, it's easy, right? Yeah. I mean, computer software, you know, plenty of computers, but you need a special software, because many software you get overflow, right? You know, the product too big, you get overflow. Yeah. So you need some special software, yeah, to, you know, you never have overflow. Yeah. No matter how do you do the multiplication, you never get overflow. Okay? Yeah. 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 So in your first project, yeah, so you have that one, overflow. Yeah. So you can use that as the background. Yeah. All right. But with that software, you do product of those two numbers. It's extremely fast. Yeah. Yeah. In a few seconds, you get a product answer. Yeah. But if you go the reverse way, want to reverse it. If you know the product, you need to do the decomposition as the product of two primes. Actually, these two large primes, these two numbers are primes, large prime. The prime with thousands digits. Okay, the prime with 1,000 digits. Yeah. Yeah. Then, the opposite way, you need to do decomposition. After you receive that huge number, you know, it's a product of two primes, but what two primes? It's very hard to get those two primes. If you go reversely, super hard. Super hard. Yeah. Multiple years. Yeah. Multiple years. So then they build an algorithm based on that to do the encryption. Yeah. Because encryption, we know, based on encryption theory, the two sides, when they need to communicate, you know, through some special encryption methods, they need two keys, right? Two special keys. One public key, one private key. Okay? Yeah. Public key and a private key. Yeah. Public key, you know, everybody, so you can broadcast. Okay? You don't care, you know, anyone can see it. Public key. Private key, then, you know, the receiving side, they need to, you know, protect it. Yeah. So put it in a secure location, you know, get it well protected. Well, private key, right? You know, so you have to have that. Yeah. So public key, private key. Yeah. Public key, you can broadcast. Yeah. Right. That, but you know, the enemy side, they can receive, because everyone can receive the public key, right? So your enemy, they can also receive the public key. Yeah. But the enemy, they do not have the private key. Yeah. Yeah. But your receiving side, they have the private key. Okay. Yeah. So they use private key, the private key. So then they apply some special mathematical theorem. Yeah. So it's a theorem in number theory called a Fermat-Little theorem. Okay. Fermat-Little theorem. Yeah. They apply that theorem, you know, to help them decompose that huge number into two prime factors. Yeah. You know, using your computer, so you can decompose. So you get two prime. But, you know, the enemy, so they cannot do it. Okay? So if they do not have the private key, so they cannot apply the Fermat's-Little theorem correctly. Yeah. Fermat-Little theorem correctly, so they cannot. If they use the supercomputer in the brute force way, right? Because if you do not have the private key, you can only apply the supercomputer using the brute force method. If they use the brute force method, then take years. Take years to decompose that huge number. Yeah. That's the idea of this RSA algorithm. Okay? Yeah. So that kind of background. Yeah. So you know, yeah, this prime decomposition is extremely hard, yeah. Extremely slow. Yeah. All right. Yeah. So the next question, we need to work on our second method, improve the method. Yeah. So here I don't have much time, yeah, but the good thing is this method is pretty easy, very short. Yeah. So we don't need much time to get a solution. That's the nice thing of the second method. Okay. All right. Let's see. the mathematical tool, but we need some special mathematical tool. Yeah. This tool is very simple. Yeah. Yeah. In your primary school, you learn how to do it. Okay? Integer division. So can you do integer division in your primary school? Yeah. Yeah. Grade school in your, yeah. So it's a division algorithm based on integer division algorithm. So what's that? Given positive integers a and b, yeah. But if positive integer, then we know non-zero. Yeah. But here we emphasize, because b is used as the divisor, so b cannot be zero. Okay, yeah, divisor. Yeah. There exists unique integers q for quotient, and r for remainder. Okay, so you can write, yeah, but the remainder should be in the range greater or equal to 0 and strictly less than b, such that a equals b times q plus r. So this is called a division algorithm. Yeah. So this is a simple result, but it is very important in number theory. Number theory, this basic result is very important. Okay? Yeah. Yeah. So division algorithm. So now we apply the division algorithm. We want to reduce the problem size. But the question, what is the problem size in this GCD problem? The problem size. Okay. GCD problem, yeah, all right. The size, yeah, here we apply it, yeah. The size actually is the maximum of these two numbers. The maximum of m and n. That is the size. Okay, the maximum of these two numbers. We define the problem size as maximum of these two numbers. All right. Now you apply the division algorithm on these two numbers, m and n. Unique to now q and r, but uniquely determined. So you have that. Then you can reduce the problem size in this way. Okay? Yeah. All right. So the key property we use to reduce the problem size. All right. Yeah. So here, GCD of these two numbers, but m we have a new expression, right? Yeah. NQ times r. Yeah. So we replace m by NQ plus r. So now we want to find the GCD of these two numbers. Yeah. But in the first number, you see that NQ part. NQ, the multiple of n. Yeah. So the good thing of that part is, if you use a fraction to see it, m over n, that NQ part, NQ over n, n cancel out. So you have the integer q out of the fraction. Yeah. So you take out that q part out of the fraction, then your fraction, the numerator of your fraction is reduced from m to r. The numerator is reduced. Yeah. All right. And this q, because it's an integer, out of that fraction, right? You take it out of the fraction. So this integer q does not have any impact on the common factor, right? Yeah, no impact. Yeah. For r and q, yeah, no impact. Yeah. Separate. You separate. Yeah. The two parts, integer part and fractional part, they are separated. So integer part has no impact on the fractional part. That means when you consider common factor, you can throw away the integer part. Because it just doesn't matter, right? Plus, if q is 1, if q is 2, 3, 5, any number, it doesn't matter regarding the common factor of, right? Yeah. So in that way, you can reduce the, the GCD. Yeah. So this NQ part is gone. So you have the remaining R part, but you want to switch, because N is larger. So you want to put a larger number as the first parameter, the smaller number as the second parameter. You reduce the problem size. Okay? Yeah. If you can reduce the problem size, that's what we need, right? We can do recursion. Yeah. We can keep doing this. Yeah. Keep reducing the problem size. Eventually, we stop somewhere. When we stop, the GCD number is there. Yeah. Because you cannot reduce forever, right? Yeah. Even if you start from two huge numbers, when you reduce, going down, at the end you have to stop somewhere. That's our destination. That stopping, that location, that place, that's our destination. All right, next time when you come, I just give you the final result, okay? To conclude the second improved algorithm. Yeah. All right, that's it.